So good day. Today I'm going to solve some problem in variable load. Number 1. From a 50 megawatts diesel power plant, the following data were obtained. Annual gross kilowatt hour generation is equals to your 246 times 10 raised to 6. Annual net kilowatt hours generation is equals to 231 times 10 raised to 6. Annual operating hours generation is equals to your 7,734. Annual average load in kilowatts, we have 31,890. Annual maximum peak load in kilowatts, we have 48,000. And the fuel oil consumed, or gallons per year, is equals to your 18.364 times 10 raised to 6. So, let's calculate or solve the annual load factor. Given the formula of annual load factor, we have the ratio of your average load and peak load. So, given the value, which is 31,890, your average load, and your peak load, we have 48,000. By dividing and multiply by 100, and it gives you an answer of 66.44%. Next, annual plant capacity factor is equals to your annual energy produced in kilowatt hours and the kilowatt plant capacity times 8,760 hours. So, given the value above, we have 231 million kilowatt hours, and your plant capacity, which is 50 megawatts or 50,000 kilowatts times 8,760 hours times, so by dividing, multiply by 100, and it gives you an answer of 52.74%. Next, we have annual plant use factor with a given formula of annual energy produced in kilowatt hours divided by kilowatt plant capacity times the operating hours. So, given the annual energy produced, which is 231 times 10 raised to 6 divided by 50,000 kilowatt, or your plant capacity times the operating hours, which is 7,734 times 100, and it gives you an answer of 59.74%. The last one, the gross fuel economy in kilowatt hours per liter of fuel. By solving from the ratio of annual gross kilowatt hour generation divided by the fuel oil consumed, and from the given value above, we have 246 times 10 raised to 6 kilowatt hours divided by 18.364 times 10 raised to 6 gallon. And by converting the gallon into liter, so 1 gallon equals to your 3.785 liters. So, cancel out the gallon, and it will give you an answer of 3.539 kilowatt hour per liter. Next problem. A power plant is said to have a use factor of 48.5% and a capacity factor of 42.4%. How many hours did it operate during the year? So, R it operates is equals to the ratio of your capacity factor and your use factor, equals to the given value, which is 42.4 capacity factor, and divided by 48.5 times 8,760 hours, and it gives you an answer of 7,658.23 hours, or approximate to 7,660 hours. Next, number 3. A 100 megawatts power plant has an average load of 60 megawatts and a load factor of 70%. Find the reserve over peak. So, given the value of your capacity, plant capacity, and the average load, let's find the reserve over peak. So, reserve over peak is equals to your plant capacity minus your peak load. By solving first your load factor or your peak load from the formula of load factor is equals to average load over peak load. So, by deriving the formula, peak load is equals to your average load over load factor is equals to your 60 megawatts over 0.70 is equals to your 85.714 megawatts. So, by solving the reserve over peak load, equals to 100 megawatts minus your peak load, which is 85.714 megawatts, and it gives you an answer of 14.29 megawatts. The annual peak load on a 15,000 kilowatt power plant is 10,500 kilowatt. Two substations are supplied by this plant. Annual energy dispatched through substation A is 27,500,000 kilowatt hour with a peak load at 8,900 kilowatt, and 16,500,000 kilowatt hours are sent through substation B with a peak load at 6,650 kilowatt. Neglect line losses. Find the diversity factor between the substation and capacity for the power plant. So, given the annual energy of your substation A and your substation B, and we have a peak load of the two substation, by solving the diversity factor with the given formula of sum of your individual maximum demand divided by maximum simultaneous demand. So the maximum demand of substation A plus your maximum demand of substation B divided by the maximum demand of power station. So given the value of the demand of substation A, which is 8,900 kilowatts, plus 6,650 kilowatts of the maximum demand of substation B, divided by your 10,500 kilowatts, and it gives you an answer of 1.48. And 1.48, that is your diversity factor. Next, by solving the capacity factor, by the given formula, with the ratio of your average load over your installed capacity. So, average load of your substation A and substation B. So, we have 27,500,000 kilowatt hours plus 16,500,000 kilowatt hours, and divided by your installed capacity, which is 15,000 kilowatts, times 8,760 hours, and it gives you an answer of 0.3349. So number 5, the system shown in figure 2 to 7, Morse page 41, consists in part of transformer serving customer E, F, and G. Estimate the peak load on the transformer. So from the book, given figure, we have here your power plant, the substation, and the feeder and the distribution transformer. So here is your E and your customer E, F, and your G. So from the for your customer E, the store building with 5 kilowatt lighting, 25 kilowatt small motor power. F, we have store building with 18 kilowatt lighting, 35 kilowatt small motor power. And G, we have your office building with 55 kilowatt lighting, 80 kilowatt large motor power. So here's the illustration. We have your transformer, your customer E, F, and G with a given consumed kilowatt. We have lighting, motor, as well as your E, F, and your G. So the required in the problem is the peak load on the transformer. So the formula on the peak load on transformer is the ratio of your total maximum demand over your diversity factor. So in order for us to solve your peak load, first we're going to find your total maximum demand. So for general power services, from the book, the typical demand factor here. So we have here your commercial lighting, stores and offices. We have here the factor of 0.70, and for general power services, we have 15 kilowatts to 75 kilowatts. We have 0.55 ang iya factor, and over 75 kilowatts, we have 0.50. And in order for us to solve the actual maximum demand, so from the formula of your demand factor, so by deriving the formula, we have AMD, or the actual maximum demand, is equals to your connected load times your demand factor. So we have here also the motor efficiency, which is 72%. From the book, we have motor efficiency assume uniformly 72% for simplification. And so we are going to solve the AMD. For customer E, we have 5 kilowatts and your 0.7, your factor, which is 0.7, plus your 25 kilowatts, your motor, divided by your 0.72, your motor efficiency, times 0.55. So it gives you an answer of 22.60 kilowatts. Next, for customer F, we have actual maximum demand is equals your 18 kilowatts times 0.7. So plus your 35 kilowatts divide your sa motor mo, divide mo sa 0.72 motor efficiency times 0.55, and it gives you an answer of 39.34 kilowatts. So for customer G, we have actual maximum demand is equals to your 55 kilowatts times your 0.7 plus the motor, which is 80 kilowatts, divide motor efficiency which is 0.72 times 0.50, and it gives you an answer of 94.06 kilowatts. So from diversity factor between the consumer, so from the book, we have here the diversity factor, which is 1.5 between consumer. So we're going to solve your peak load. So the total maximum demand of these three, which is 127.57 kilowatts, divided by diversity factor, which is 1.5, and it gives you an answer of 104 kilowatts. So assume the maximum feeder loads of the system shown in figure 227 Morse in page 41 are 18 kilowatts for your feeder 1, feeder 2, 225 kilowatts, feeder 3, 115 kilowatts, feeder 4, 95 kilowatts, feeder 5, 37 kilowatts, and feeder 6, we have 45 kilowatts. Predict the peak load for the power plant. So from the figure in the book, so we have here power plant, substation A and your B, and we have here the feeder 1, 2, 3, 4, 5, 6. Given the value assigned in the feeder, so first, in order for us to solve the peak load, we're going to get the average load of all the value of all your feeder. So by getting the summation, it gives an answer of 565 kilowatts. And next, since we're going to find the diversity factor, given the value of your diversity factor for feeders, we have 1.2. Diversity factor of substation, we have 1.5. Since it is in between of substation, let us include na to in 1.1. So by solving, we have peak load is equals to your 565 kilowatts, your average load divide your diversity factor, which is 1.2 times your 1.1, and it gives us an answer of 428.03 kilowatts. A hydraulic storage plant has a unit similar to that shown in figure 2 to 15, Morse, page 57. The efficiency of generator motor is 96%. The turbine, which is 80%, the pump 75%. Average elevation between upper and lower pools equals to 30 meter. Assume a 2% loss of head in pipe friction. This unit was installed to carry a daily peak load of 1,400 kilowatt hours. There's a daily evaporation loss of stirred water amounting to 907 tons. Calculate the overall efficiency of conversion. So we have here the given, the generator efficiency 96%, turbine efficiency 80%, pump efficiency 75%. Your average elevation in upper and lower, we have 30 meter, head friction loss 2%, peak load 1,400 kilowatt hours, and we have here your mass, which is 907 tons. So by conversion, your evaporation loss, which is 907 tons, converting to kilogram, your 1 ton is equals to your 1,000 kilogram, so it gives us 907,000 kilogram. So by solving the volume flow rate, so we have mass over your specific weight of your water, which is 907,000 kilogram divided by 1,000 kilogram per meter cube. So it gives us an answer of 907 meter cube, your volume. So cancel ang kilogram. So for your turbine, head of your turbine, we have head is equals to your gross head minus your head, your friction head. So given your head, which is 30 meter, minus your head friction loss, which is 2%, we have 0.2 times 30 meter, and it gives us an answer of 24 meter. So from the formula of your output power is equals to your specific weight times your volume flow rate times your height times your generator efficiency times turbine efficiency. So 9.81 kilonewton per meter cube times 24 meter, your height, times Q1 times 0.96 times 0.80, your turbine efficiency equals to your 1,400 kilowatts hours. So by converting your hours in seconds, so we have times 3,600 seconds. So cancel out the ang hours, ang kilonewton, and the meter, and your second. So ang mabilin na unit is meter cube. So it gives us an answer of 27,873.34 meter cube. So for pump, solving for the head, we have gross head plus your friction head. So your head is equals to your 30 meter plus your friction head loss, which is 0.2 times 30 meter is equals to your 36 meter. So power of pump, we have specific weight times your volume flow rate times height divided by your generator efficiency times your pump efficiency. So we have here the power is equals to your 9.81 kilonewton per meter cube times 907 meter cube times 36 meter divided by 0.96 times 0.75, and it gives us an answer of 444,883.5 kilonewton meter or kilojoule. So by solving the net power equals to your power of your turbine minus the power of your pump is equals to your 1,400 kilowatt hours. By converting your hours in seconds, we have multiplied it in 3,600 seconds. So cancel out the hours and the second. So mabiling ng unit is kilonewton meter minus 444,883.5 kilonewton meter, which is the power of your pump. So it gives us an answer of 4,595,116.5 kilonewton meter or kilojoule. So overall efficiency is equals to your power net is equals to your specific weight times your volume flow rate times your gross head. So 4,595,116.5 kilonewton meter divided by your 9.81 kilonewton per meter cube times 27,873.34 meter cube which is your volume flow rate, your volume rather, times 30 meter times 100. So, cancel out the meter cube, the kilonewton, the meter. So, wala, bilhin ni unit, times 100. So, it gives us a total efficiency or overall efficiency of 56.02%.